Welcome, Lee, and welcome everybody to the Taurus Report. So this week, last week or the week before, marked 1 year since we first started getting these new images from the James Webb Space Telescope. In our literature and stuff, we say JWST quite often. So if that's what we say, then you'll know what we're talking about. And so I was hoping to discuss this today with my colleague Lee Greer. He's joining the Taurus Report. And Lee is the scientist who put up and maintains the enlightenmentlegacy.com website, which I'll be sharing some links from there as we discuss all this. So as is usual for the Taurus Report, I put all the links in the comment. For any sites that we discuss, the links will be in the comments, so you'll be able to access all of that. Lee and myself, we have a few things in our outlook that are in common. First, we question the hot Big Bang cosmology, the LCDM cosmology, and we both feel that something new is needed. Maybe it's not totally clear quite yet what exactly that will be, although obviously we have some ideas. But the main thing is, I think we share the view, Lee, that we really need, the scientific community really needs to move in a different direction in a big way on all this. And so a year on since JWST first started giving us all these images, which we feel kind of challenges standard cosmology, and we were kind of hoping that maybe more scientists would feel that way. There's a few that do, but by and large, it seems like a lot of the community has sort of kind of shrugged their shoulders at it. And so, Lee, I guess what I would like to start with is just to ask, in your opinion, the things that we first saw from JWST that, in your opinion, most challenge standard cosmology.
Right. Well, I think some of the things that immediately stood out very quickly within the first few days of their releasing papers is the fact that that as far as you looked out there seemed to be a lot of fairly normal morphology galaxies that stretch off into the distance. I've heard figures as many as, and the number of galaxies is very large too, 100,000 times more than expected from the ordinary merger hypothesis beyond, out in the high redshift zones beyond z equals 10 approximately.
Right. So to just give a little bit of context for anybody who might be a layperson and just kind of curious about all of it, just to give some kind of idea, like for the Milky Way, it takes something like 200 million or 300 million years for the galaxy to make one rotation.
Yeah, about 250 million years, as I understand it.
And so then if we're talking about a universe that's 13.8 billion years old, that's not too many rotations. And so the way standard cosmology approaches it, one would expect that as you start looking back and you get closer and closer to the supposed origin of all this, the Big Bang, yes, you would expect the universe to look quite a bit different than it does now the closer you get to the Big Bang. And that's basically what you're saying.
That's correct. Well, the standard theory, there are a number of things. The standard cosmology, which is the lambda cold dark, we call it the hot Big Bang, but it's the lambda cold dark matter version of the hot Big Bang, because of the thermalization and the black body radiation and many other interpretations of parameters in the early universe. Galaxies were supposed to have built up by mergers during the time of reionization.
Mm-hmm.
So the surface of last thermal scattering last scattering is supposed to be about 380,000 years after the Big Bang, and that's supposed to give us the cosmic microwave background radiation.
Right, that's the CMB that is supposedly the background of everything else as we look out into the cosmos.
Exactly. And this background is supposed to, within a few tolerances, be equal to a black body curve,
Mm-hmm.
which is what the type of radiation which comes from a body in full thermal equilibrium,
Mm-hmm.
which is a very high tolerance to have right at the beginning of an explosive universe, to have everything.
Yeah, that's an aspect of it that I as you know, in my own theory, CGC, I maintain that what the CMB actually is the outer reaches of the universe that are in full equilibrium with the interior universe, in that no radiation can escape the universe, according to my belief. And
Yes.
so, whatever goes into those outer reaches, as far as energy, that same quantity comes out. And so, the outer reaches are actually a perfect black body, in my view. But if you're saying that they represent the hot Big Bang, it never really has made sense to me how that could be considered something in equilibrium. I don't really understand that.
Well, I think what the part of the issue is there, they needed something to thermalize it to that level, and that was part of the motivation for the invention in 1980 of the inflationary hypothesis by Alan Guth and other people, where he basically said, Guth's argument was, well, and he did have work that he did with others. Of course, he had a lot of help with that. He published a paper in 1981 in the Physics Review Journal D called "Inflationary Universe: A Possible Solution to the Horizon and Flatness Problems." Okay, because all of the old Friedman, the earlier Big Bang models, Friedman, Lemaitre, Gamow, and so forth, they simply did hypotheses, but Guth set out to solve the problem. If you look back in time, time goes back to zero, temperature goes to infinity. That means it's
Right.
undefined for and no theory exists which can define it. And
Right, because
and
the density and temperature, which is kind of funny, but density and temperature, both are going up.
That's right.
For practical purposes, to infinite levels, the closer and closer you get to the hot Big Bang. Yes.
Correct. It's supposed to be on the order of the Planck mass, which is about 1.22 times 10 to the 19 giga electron volts. So this huge number, and it went into thermal equilibrium. It cooled. It did a supercooling where it as it spread. It's called a supercooling that was higher than, sort of like a false vacuum above the regular vacuum background, and that cooling, that rapid supercooling, caused this very rapid expansion and smoothed out the matter energy context.
Right, and that's inflation, and of course inflation was not ever observed, but it is something that is posited, because otherwise it's very difficult to explain everything else under this standard theory. If you don't have inflation, there's a lot of things that are very difficult to explain. And so inflation, in my opinion, is thought up to save the theory. Okay, we need for this to have happened, otherwise we can't explain a lot of this stuff.
Exactly. We've got what is called the horizon problem and the flatness problem. How do you get down to such tolerances where the curvature of the universe approximates a Euclidean, very close, a Euclidean flat surface, if it all came from one location, and then once, if it has all come from one location and the universe is expanding outwards, then you're left with the horizon problem. There are going to be parts of the universe which are in reasonable communication with each other, where the predecessors of those parts are causally separated in time. There would never have been time following the rules of special relativity for
Right.
for an effect to even out across this whole field of view.
So we wouldn't have the homogeneity that we're seeing.
Correct. Correct. You wouldn't have the homogeneity, and the homogeneity is doubtless connected with the thermal smoothness, the thermal equilibrium of this black box radiation, of this supposed perfect black box black box radiation,
Right.
black box radiation.
Right, right. Okay, so with JWST, then the first thing that was very challenging is they look back, the universe seen from the images we were seeing in the past, it looked very much like what the universe looks like now, and we also had these massive galaxies in the sense of we weren't expecting these standard galaxies like what we have now to be fully formed in that first billion years.
Right.
So that was the second thing that JWST showed that was challenging the standard cosmology.
Yeah, let me make a couple other statements
Okay.
too
Okay.
about that, because it's important to understand so much of this is tied together with this field that was postulated by Alan Guth and other inflationary cosmologists, which gives us the basic parameters for if you make certain adjustments, you can solve parameter issues which arise in an ordinary Friedman equation type universe, so Robertson, Walker, Lemaitre, Friedman universe, right?
Mm-hmm.
And of course, there was also the problem. Some problems have gone away, like the question of charge parity, symmetry. That there should be monopoles and equal amounts of antimatter and all of that stuff in there, right?
Right.
Well, the consequence and the breakthrough which he saw was that when this period of cooling went down from the time it started, and it's in a few orders of magnitude of the fraction of a second there, the universe cooled by 28 more orders of magnitude, which is...
Right, in fraction of a second, yes.
Yes, right. Which it was supposed to have done.
So this is the kind of thing that we just have to accept on faith, because otherwise the whole theory falls apart. So, yes.
That is exactly right. We've called it the sorcery of reading the CMB radiation. So.
Right. That's right. So, okay, and then let's see. There were a few other things that we had discussed here. The fact of basically stretching space. We had mentioned that according to standard cosmology, once Einstein's expansion factor that was tacked on to general relativity, once that came to be interpreted as space itself stretching, there were some logical consequences to that, and one of which is that normally when we look at objects, as they get further away from us, they get smaller.
Yes.
And that's just standard. I'll even call it common sense, day-to-day experience of everyone.
Yes.
But if the expansion rate idea is correct, that space itself is stretching. Now, in normal scales, we would not notice it for anything close to us. Okay, but when you start getting to intergalactic scales, it becomes significant. And in that case, once you start getting out, and I forget the exact, how far exactly, I think something like Z of 8 or 6 or something like that. Once you get out far enough, then actually the angular size of something at those distances, as it gets further, will not shrink as it gets further and further away from us. Its angular size should stay the same,
And even grow a
grow
little bit, right?
and even grow a little bit. And that's just a consequence of believing in this stretching space idea. And one of the things that the Webb telescope did not show was this. We have galaxies that appear to get smaller, angular size, appear to get smaller with distance, even beyond that. Okay, and so one would think that when you see that demonstration of that everyone would say, okay, well, then expansion of space is disproven.
Well, exactly.
Yeah.
Sorry, go ahead, Joe.
Yes,
Yeah.
and that's the kind of thing where I am very much disappointed. It's like we keep seeing all these things contrary to what standard theory predicts. And
Yes.
it just seems like anything that contradicts standard theory is just everybody just stops talking about it. So
Yes, sadly. I mean, what one can say about that, because everything is closer, as you mentioned, uh, the angular size of the galaxy should appear larger. But we were not seeing that even under the old Hubble Space Telescope. However, the James Webb has made it 2 to 3 times smaller, these galaxies, as far as their angular size, and they basically come close to a sort of Euclidean fall away almost, as far as the what you would expect to see in a universe where redshift is proportional to distance. You know.
right. Yes, and so that is another thing, and then we keep seeing. It seems like every week some new thing comes out where scientists in various ways try to save standard theory. I believe my last Taurus report, I talked about how with the metallicities that we're seeing,
Yes.
some theorists were positing that there were some early supergiant stars, which we don't
Right.
see because they're incredibly short-lived, supposedly.
Right.
And these supergiant stars were able to create in fast motion all these metallicities that we're seeing. Whereas
Yes.
in our observed experience, as we look around the universe, we see stars go through a kind of a set life cycle, and we got a pretty good idea of how long it takes to get these kinds of metallicities. And so they had to come up with sort of exotic things to try to explain it at the beginning. But again, the exotic things that they come up with are not observed; they're just posited.
That's correct. That is absolutely correct. If I may share a screen briefly, I wanted to show
Sure. Yes, please.
about just a second here. Let me find the right spot. Okay, and I have a screen share, and there it is. Here is what some of. Sorry, it's a little bit
No, it's
there.
perfect. I can see it. It's good.
Okay, good.
Very good.
Here is what the background radiations are that are observed in the universe, going from.
Yeah, excuse me, Lee. Could you say what is on the vertical axis and what is on the horizontal axis?
Sure, absolutely. On the vertical axis is the log intensity of the radiation that we find in these backgrounds or in the discrete sources.
Uh-huh.
Along the horizontal axis is the log frequency.
Mm-hmm.
Okay, and so you go all the way from discrete radio sources all the way down to hard gamma rays. So here are discrete radio sources. Here is the cosmic this is the microwave background radiation. There's an infrared background radiation, an optical, the ultraviolet part, soft X-rays, hard X-rays, soft gamma, and hard gamma, going all the way up here in a log.
So as you move to the right, you get higher energy waves.
Higher energy and higher frequency.
Right.
Correct. Now, for some reason, the there is a picking out of the microwave part of this background as being of cosmological significance, and the rest of these tend to be not discussed as being cosmologically significant. So just wanted to draw your attention to that. But if we actually look at the small anisotropies which are in this is from the 1992 COBE view. This is about 27 thousandths of a degree, these variations between the hot pink and the blue, you see. And that was improved by the Wilkinson microwave anisotropy map here, greater clarity, and then ultimately by the Planck map. So here's COBE, the Wilkinson anisotropy map, and then the Planck.
Steady improvement.
A steady improvement and a seeming more discrete number of sources. Okay. Now, for a while, they thought, oh, there's a polarization signal in there, meaning the way that because the electromagnetic waves in a classical sense are perpendicular to each other, and so that they thought there's a polarization there, and they said that's a prediction of the inflation, and there was a lot of excitement, and people thought, okay, we're about to give some Nobel prizes for inflationary theory and all of that stuff. But and there were astronomers who were appalled by how not poorly the data were vetted. It turned out that the polarization seemed to be an artifact of interstellar dust within our galaxy.
I see. And just for people who may be watching, polarization, light has an orientation.
Correct.
So what you would expect, or what I would expect, I should say, is for the light coming from distant sources to be of all different orientations. So just would be randomly oriented. So when the light hits us, it would be randomly oriented every which way. Well, like totally random. Now, if it hits us and its orientation is not random, that's what we mean by polarized light. And it can be polarized to different degrees. But if we're expecting random and we see some pattern in the orientation of the light, then that is what Lee is talking about here. Sorry for that interruption.
Oh, yeah, no, that's great. That's great. Now, here's what this spectrum, this is called the power spectrum. This line right here is supposed to be the black body curve, and then there are supposed to be waves from different events. They're called baryonic acoustics, the type of echo of the transitions that happened there in the early universe.
I'm sorry, Lee, but might I interrupt again just to, if you could go back to that drawing, and I just want for the viewers to explain a little bit what they're looking at here. Yes, so this is what's going on here. If you look out at the universe, you will notice that your light sources, they kind of clump together, and scientists have different ways of evaluating what I am going to call clumpiness. Okay. Yes. And so you have little teeny clumps and you've got big giant clumps. And what this power spectrum does is, now I want to look here. I have to be careful because I got to see which end is the big clumps and which end is the small ones. I think to the right are smaller clumps.
Smaller, yes. Correct.
Okay. So what this means is when you see a peak right here, it means that you see a lot of clumps of this particular size.
Yes.
Okay. And when you see this peak here, that means another set of clumps in the universe, clumps of light sources of another different size. And so this is how common different size clumps are in the universe. And so again, Lee, sorry for that interruption there, but please proceed.
That's perfect. And what you see as you go across there is kind of, with the multipole parameter, is how the the anisotropies vary as you go down this scale. This is what's observed, and they try to fit parameters to make it so they can explain all the ups and downs of this acoustic spectrum peak.
That's right. So they throw in things like dark matter, they throw in things like dark energy, they throw in baryonic mass and gravity from that, and temperature and various things to try to be able to predict this shape.
Exactly. I believe I have an animation down here which
oh, that would be great. Yeah.
Yeah, let me see if I can get it right. So, all right, well, wait. I can find it a little bit later but let's see. All right, well, okay. So now the problem is, suppose, what gives us the right to think? Let's just go back to the spectrum at the very top. Here's some of that polarization issue, right? Okay, which they thought was primordial. They're called B modes, but there actually turns out, this is from the BICEP2 data experiment, it actually turns out that this is the mundane explanation of dust in the galaxy. You know?
Yes, and so this diagram is showing ways in which light is oriented as it comes towards us. And correct. So they found that the dust explained this.
Yes, that they could not rule that out as what was causing it. And Brian Keating of UCSD occupies the chair of Jeffrey Burbidge from before in astronomy. He wrote a book called Losing the Nobel Prize, and because he was part of the experiment. And when they found out that this did not predict that this did not arise from the predictions of inflationary theory, but it was dust, it became very clear that it was all overhyped. You know.
Right.
So, let's see. One thing that you can say, if you're going to have all of these little anisotropies here, why not just recognize that in many ways these anisotropies fit objects in the nearer universe? That maybe many of these anisotropies are not generated primordially, but in the more recent universe, as you would expect with pretty much all the rest of the spectrum, right?
Right. In other words, it's coming from stuff within the universe.
Correct. Not at some pristine place where it's unaffected by the transmission across the light years. You know. I can stop sharing if you want to take it somewhere else. I may find that animation in a minute. So.
All right. That would be fine. So just a few things that I had wanted to mention, and I am going to. Maybe I should share screen so that you can see it. I mean, let's see here. Let's share. All right. Now I am sharing screen.
Okay.
All right, so let's go to some of the things. I just want to mention some of the articles out there of various scientists trying to deal with what JWST is seeing, and also in this case trying to deal with the Hubble tension. Okay, so it's articles like this that I'm seeing crop up all over the place, where, and I read this article, and in this case, the scientist is explaining how the Hubble tension may be satisfied by introducing a new parameter where, and I am going to kind of facetiously define it as where whatever era that we look back, whatever we need the expansion factor to be to explain what we're seeing, then we just come up with a mathematical way of varying that expansion factor.
Yes.
Depending on era, and it's like it's a dynamic expansion factor, and so it is introducing another parameter that can be manipulated. And I like on your website, Lee, where you
Yes.
show that this, okay,
Yes.
where Lee did this cycles within cycles to show how, if you have enough parameters to play with, you can make basically anything you want to happen. You can claim
Yes.
it's just the natural operating of the universe here. And so, in my view, this is the kind of thing we're seeing where scientists, rather than allowing their standard theory to be disproven, instead
Yes.
they just keep introducing more and more epicycles into it to try to save it. So this is one example. Now, another example is this article here. And again, all these links will be in the comments here. And this one, Lee, you and I discussed last week a little bit too. So a scientist came up with, looking back at the results from Webb that we just discussed, about how we're looking back and we're seeing galaxies that are the wrong size if we're to accept the predictions of standard cosmology about the expansion of space. We're seeing galaxies that are the wrong size. And so here, the scientist is proposing that, well, maybe the universe is, closer to 27 billion years old. 27
Yes.
billion years old, as opposed to 13.8. Now, I do like the fact of being open to saying, okay, well, there has to be a major change from standard cosmology. And another thing that I liked about this article is that they did hold out for something which I have argued for, which is the fact that tired light may be able to explain part of the redshift. Now, of course, I believe the redshift has two components. One is that galaxies are, in fact, in general, moving away from us, accelerating away from us. And also, I also claim that tired light is causing part of that redshift, although not all of it. And so I liked the fact that the article did that, okay?
Right.
And so the thing that I don't like about it is that he still keeps a lot of the redshift due to the stretching of space,
Yes.
which I don't like that. He still keeps the Big Bang idea, and he gets around the difficulties by claiming that physical constants mutate with time. Okay, so
Right.
various
Like
like coupling constants and everything else. And of course, this brings us back to something you and I keep complaining about, or I don't know if that's the right phrase, complaining about, where, as I was saying, a thing that we've kind of both been complaining about is that when scientists propose fixes which are unobserved,
Yes.
right? They're unobserved, and that's what inflation is. It's things that are unobserved fixes that make everything come out right. And it's my difficulty with that. And I teach mathematics. I teach calculus and statistics. And so I'm a fan of math, but there is a subtle difference between a mathematical exercise and science. I mean, of course, science must express itself in consistent mathematics. I think everybody would agree with that. However, just because you can construct something to be mathematically consistent, that doesn't mean that it's real. So that's a point that I like to make. In any case, Lee, is there anything else you would like to share tonight?
Yeah, well, I just wanted to point out that that drawing there, as beautiful as it is, and it illustrates what I was pointing out. That drawing is not mine, which I have on the front
Oh,
page.
the pi.
Right.
Right,
Yeah.
on your website. Yes, that's right.
Correct. It is not mine, but I very much value the contribution it makes to understanding this.
Right.
Yeah. So
If you have enough parameters, you can make anything happen.
you can make anything happen. And one of the things that is there is there are you know, on the acoustic oscillations, I link it there. There are whole software packages where they try to have parameters that they can adjust to match the oscillations that they see within the cosmic microwave background.
Right.
You know, so that's let me. I'm going to see if I can find that animation really quick here. It's in another chapter, one that's not posted yet. Okay. Here, here we are. So if I may,
Yeah, share it. Go ahead and share.
briefly, there we are, right there. Notice that there you start on one side, you know, on this side here with the modes, you know, with the big modes, and then you go to finer and finer tuned modes, and see, like that's the map of the cosmic, you know, the multiple elevation at those angular at those angular increments.
Uh-huh.
And what you see, they are trying to find different ways to run the monopole, which, as I understand it, is a Fourier transform of the spectrum, right?
Uh-huh. Fourier transform. Yep.
Yeah, exactly, to make it fit what is observed. And there's slight distances. If it's a hyperbolic universe, it looks a little bit different. If it's a flat one or a closed spherical universe, you have a different pattern within that, you know, and all of that. So there's all these parameter adjustments which have to be made to make this thing work. It's important to recognize that a lot of people today are questioning how primordially significant the CMB really is, and how much it reflects intermediate matter.
Because a lot of standard cosmology is just based on that interpretation of the CMB. It starts there. That, and I would say the other big thing is the fact of the redshift of most galaxies. So those two things, I guess, would be the twin pillars that are kind of holding up standard cosmology. Those two interpretations of those things.
Yes.
So.
Yes. That's correct. And then there's the whole issue about structure for formation. Where are all the mergers? How come there are chemically, you know, metallistically mature galaxies which appear very, very, very early? There seem to be a number of problems.
Oh yes, that was another issue, is the metallicity that we're seeing in these very early galaxies.
Correct.
Yes, that is another issue.
And then what are supposed to be the primordial abundances of some of the light elements? The lithium-7 abundance is basically a factor of 20 times off.
Yeah, now that is another. I seem to have a lot of pet peeves, Lee, and I run into these pet peeves because I actually have had experience arguing about these things and all of this, and something that has people have used to kind of counter my arguments a number of times is the abundances, elemental abundances, you know, and they'll say, well, you know, standard cosmology can predict deuterium and your theory can't, and it's like, and I have to respond like, well, with my theory, I am one person, and I haven't really, I'm not like thousands of scientists working for 100 years. to construct something. I'm just one person. And so I haven't really looked at the deuterium thing. But if we're going to go there, if you're going to say that deuterium proves your cosmology, then I can say that lithium disproves it.
Yeah.
And so it's like, you gotta, it's the old thing about being falsified, right? Where you have to explain how your theory is falsifiable. And if you're going to drag in deuterium abundances, to kind of shore up your idea, then you've got to deal with lithium abundances.
Well,
and so then it's like, yes.
Plus, in a paradigm, if one aspect of a hypothesis fails, the whole thing fails. You're not supposed to have all the parts right except for two or three.
Right. Yes.
You've got to make predictions across the board. Otherwise,
all it takes is one to disprove it.
That's exactly right. Now, one of the things that has also emerged, if I might mention one last thing, if it's okay by
you. Sure.
Is there is phenomena in the cosmic microwave background which suggests that there are large-scale features, sort of like concentric circles, which extend where there is reduced anisotropy in temperature, which extend across 8 degrees of the sky. These are huge. If this was the surface of last scattering since the Big Bang of 380,000 years after the Big Bang, then these structures are even these lowered anisotropy concentric circles are much lower, are much larger than some of the largest galactic and quasar structures that we know about in the universe. What causes that? It doesn't fit the lambda CDM. Of course, Roger Penrose has his own theory about what can cause these rings and so forth, and there's disputes about them and everything, but it suggests, again, that there's a problem with ascribing the terribly smooth anisotropy and homogeneity and all of that across the universe as the Big Bang demands.
Right, that's right. Yes, and so to just a few things I'd want to point out to viewers who might not know the terminology. Anisotropies. An isotropy just means a kind of a sameness.
Yes.
So if things are isotropic, it means they're the same. Anisotropic means that you see differences. Okay,
and with isotropy, it's particularly angular differences. It's not the same as homogeneity. It is angular differences. Does the sky look the same in that orientation as it does in that angle of view?
Yeah. Right. So yes, and so there just are a lot of challenges here, and I just feel that as we've iterated several times tonight, that the response of most cosmologists is to introduce epicycles to the current theory.
Yes.
And I just feel that this is a very unproductive direction for most cosmologists to be going towards, where what needs to happen is for them to say, okay, this GR-LCDM Big Bang thing is disproven, and we need to start trying to construct something else to take its place. And that is sort of what we're rooting for, I think. So.
I believe so. Yep.
Okay. All right, Lee. Well, I want to thank you so much for joining us today on the Taurus Report. And
thank you so much, Joe.
For everyone watching, I am going to put Lee's site in the comments again, and I really recommend going through it because he has done a ton of work, and there is a lot there. It would take quite a bit of time to get through it all, and it's all relevant to what we're talking about. And so thank you all very much for joining us today, and we will see you next time on the Taurus Report. Bye-bye for now.